In this notebook, we will clarify the two distinct meanings of the word dimension in the context of machine learning. The first usage of dimension refers to an attribute of the data structure used to store data, such as a tensor. A tensor is essentially a multidimensional matrix. The term dimension in this context describes the number of indices required to locate an element within a tensor. The second usage of dimension refers to an important property of data itself. It is often used to describe data that is input into a machine learning model. Here, dimension refers to the number of features that constitute the input data. The same term dimension is used to describe both the data and the data structure that holds the data. However, the context in which the word is used clarifies its meaning. A few examples will illustrate this. So let's download a dataset made up of grayscale image of handwritten digits. A grayscale image is essentially an image made up of shades of black and white. This dataset is typically used to train models to classify an image containing a digit. Each image in this dataset can be stored in a two-dimensional tensor, made up of 28 rows and 28 columns. Each element of this tensor is a pixel value that ranges from 0 through 255, where 0 represents black, 255 represents white, with all numbers in between are shades of gray. Here we are looking at all the numbers in an image that contains the number 5. We can visualize the number 5, even by eyeballing the raw data in this tensor. Most of the pixels are 0 or black, and all the non-zero values are roughly in the shape of 5. This is a two-dimensional tensor. The shape of this tensor is 28 by 28. This means there are 28 numbers along each dimension or axis. In the context of tensor shapes, each dimension is also referred to as an axis. For instance, tensor operations implemented in libraries like PyTorch refer to each dimension as an axis. Now, the second interpretation of dimension refers to an aspect of the data itself, which in this case is the total number of individual pixels in a single image. This image has 784 pixels arranged in 28 rows and 28 columns. Each pixel represents a feature of the input. The phrase, dimensions of the feature space, refers to the total number of features of the input. Despite being simple grayscale images, this dataset is considered high-dimensional because it has 784 features. In summary, from a data structure or storage perspective, we only need a two-dimensional tensor to store an image. This two-dimensional tensor contains high-dimensional data, with 784 features, where each pixel is a feature. An implication of high-dimensional input data is that the number of possible inputs to a model can be large. For instance, the number of possible images that can be created with 784 features, where each feature can take on 256 values, is a number several orders of magnitude larger than the estimated number of atoms in the universe. The two examples below are to get a feel for tensors. Tensors are the backbone data structure of machine learning. They are used to represent input, output, as well as model parameters. Input data such as images, text, and audio have a large number of features. This is often referred to as the curse of dimensionality. A large number of dimensions is considered a curse due to the challenges they pose for training models on such inputs. One challenge is model complexity. For instance, to accurately model the distribution of high-dimensional data, in many cases, an extremely complex model with a vast number of parameters is required. This complexity makes the model challenging to train and increases the risk of overfitting. Another challenge is data sparsity. Despite the large number of potential images, the actual number of images available for training is finite, and often relatively small, compared to the space of all possible images. This results in sparsity in the data distribution, with many potential images not being represented in the training set. However, it is also important to note that not all potential images occur naturally. We can leverage this fact to ensure that the training data primarily represents images that naturally occur. Another challenge is computational constraints. Handling high-dimensional data demands significant computational resources. Training models on this data can be exceptionally resource-intensive and time-consuming. Lastly, assigning probabilities to inputs in high-dimensional data is challenging. Generative models approximate the underlying probability distribution of the input data space, either directly or indirectly. They must learn, or at least approximate, this underlying probability distribution to generate new samples. It's important to note that the immense size of the feature space makes it practically impossible to assign probabilities to each possible image, necessitating the use of approximation methods. Despite these challenges, in some cases, it is possible to train even simple models to classify digits with high accuracy. Typically, this is achieved by training a model on a fraction of the 70,000 images and then testing it on the remaining fraction. In future notebooks, we will explore how to achieve high accuracy in classifying these digits. The models we'll examine are neural networks, which perform quite well with high-dimensional data. In this context, dimension refers to the feature space. They accomplish this by reducing the dimensionality of the input feature space, or in other words, by condensing features. It is worth noting that there are approaches to classifying digits without using neural networks. However, they do not scale as effectively as neural networks to handle large datasets with high-dimensional inputs, even though they offer other advantages, such as interpretability and model simplicity.